Hello chemistry students, Dr. Tullis here. In this section we will write equilibrium constant expressions for acids and bases, understand the relationship between Ka for an acid and Kb for its conjugate base, calculate pKa from Ka or Ka from pKa, and understand how pKa is correlated with acid strength. So acids and bases can be divided roughly into two groups: strong electrolytes like hydrochloric acid, nitric acid, sodium hydroxide, and weak electrolytes like acetic acid and ammonia. Hydrochloric acid is a strong acid, so 100% of the acid ionizes to produce hydronium and chloride ions. But in contrast, acetic acid is a weak electrolyte because it ionizes only to a small extent in water. One way to look at the relative strengths of acids is to measure the pH of solutions of acids of equal concentration. The lower the pH, the greater the concentration of hydronium ions, and the stronger the acid. So if I have a pH of 1, that is a lot greater concentration of the hydronium ion, and it's a lot stronger acid than an acid that's a 3 or a 4 or a 5. Similarly, for a series of weak bases, the hydroxide ion concentration will increase. The pH will increase as the bases become stronger. So a pH of 14 has a stronger hydroxide concentration than a pH of 8. For a strong monoprotic acid, the hydronium ion concentration in solution is equal to the original acid concentration. So if I said I had 0.1 molar HCl, that means I have 0.1 molar of my hydronium ion concentration. The same is true for a strong monoprotic base. The hydroxide ion concentration is equal to the original base concentration. If I said I had 0.1 molar NaOH, that is a strong base. So its OH concentration in this case would also be equal to 0.1 molar hydroxide ion concentration. For a weak acid, the hydronium ion concentration is much less than the original concentration. So the hydronium ion concentration is smaller than if the acid were a strong acid. I can't say a 0.1 molar acetic acid does not have 0.1 molar of hydronium ion concentration. It would be a lot less. Same with a weak base. It would give me a smaller hydroxide ion concentration. 0.1 molar ammonia is not 0.1 molar of hydroxide ion concentration. The strength of a weak acid can be expressed with Ka. The strength of a weak acid is related to its equilibrium constant. If I have a weak acid in water, we know it's in equilibrium. We know that acid is going to donate a proton, leaving me with H3O plus and that conjugate base. So when I write my Ka expression, because this is acid, I have my hydronium ion concentration times the concentration of that conjugate base all over the original acid concentration. This is set up just like we've done in chapters before, where we take our products divided by our reactants, HA. We don't include liquid water. We can look at a weak base by expressing it with Kb expression. We take our weak base in water, and that's in equilibrium with, remember, bases are proton acceptors, so it's going to accept an H from H2O, and then that H2O, since it got rid of that H, is going to leave us with our OH minus. So we take the OH minus times the conjugate acid, all divided by the concentration of that weak base. Ka and Kb values are for weak acids and weak bases. Ka and Kb values always have values that are smaller than 1. Acids that have a larger Ka are stronger than the ones with a smaller Ka. Similarly, bases with a larger Kb are stronger than the ones with a smaller Kb value. Most acids and bases are considered weak. We already know that strong acids and strong bases almost completely ionize in water, 100%. So they have a very large K value. And because they're strong, they are product favored. Weak acids and weak bases do not ionize completely in water, way less than 100%. They have a very small K value, much, much less than 1, and they are reactant favored. This chart is going to come in handy, and we will refer to it a lot. These are a lot of Ka and Kb values for weak acids and their conjugate bases. Notice the ones that are large are the strong acids. And then we have all of our small values. Notice they're all to the negative exponent, so that means that they're smaller than 1. 1.2 times 10 to the negative 2 is equal to 0.012 molar. That's a lot smaller than 1. And notice that as I go down, those values get smaller and smaller. Those strongest acids are in the upper left. They have the largest Ka values. And those Ka values get smaller when we go down the chart, and the acid strength gets weaker. The strongest bases are in the lower right. They have the largest Kb values. If I went back, notice that my Kb values are over here. They're very small compared to my acids are very large, so they're flip-flopped. Those Kb values get larger when we go down. The weaker the acid, the stronger its conjugate base. So the smaller the Ka value is, the larger the value of Kb is. And here's the other half of that chart. We can see on the left here the increasing acid strength. As I go up, my acid strength gets stronger. So if I wanted to compare ammonium versus hydrocyanic acid, because ammonium is higher up in the list, it is a stronger acid. And we can see on the right, we can see our base strength increases as I go down. How can you tell whether an acid or a base is weak? Well, it's easiest if you can just remember the few that are strong. If it's not strong, it's weak. Here's how I remember my strong acids. If you can remember CSI on NBC, if anybody ever has watched the TV show CSI, if you can remember CSI on NBC, and we have HCl, so above on the top are all of my H's for acids. So I have HCl, hydrochloric acid. I have H2SO4, sulfuric acid. HI, hydroiodic acid. And then our NBC stands for nitric acid, HNO3, hydrobromic acid, HBr, and HClO3 and HClO4, which is chloric acid and perchloric acid. Those are all of our strong acids. Those ionize 100%. If it's not one of those, it's a weak acid, and we would find it on the list. Common strong bases, pretty much anything that's a hydroxide. Lithium hydroxide, sodium hydroxide, potassium, rubidium, cesium hydroxide, even strontium hydroxide, barium hydroxide. Here it says that neither magnesium or calcium hydroxide dissolve completely in water, but some texts consider them strong bases. So you see a hydroxide, it's strong. Now many chemists use a logarithmic scale, this looks familiar, to report and compare acid strengths. So our pKa is equal to the negative log of the Ka value. The pKa of an acid, just like the pH is the negative log of the hydronium ion concentration. So we would look at acetic acid, and it has a pKa value of 4.74. If I were to look at acetic acid on that chart, going back to this table, here's acetic acid. It has a Ka value of 1.8 times 10 to the negative 5. So if I take the negative log of 1.8 times 10 to the negative 5, I get a pKa value of 4.74. And the pKa values become smaller as the acid strength increases. So if I looked at HCO3 minus, HClO, and HF, this is my smallest pKa value, and it is the strongest weak acid in the three of these. Here's some more relationships we can look at. The product of the Ka for an acid and the Kb for its conjugate base will be equal to Kw. We know Kw is that 1 times 10 to the negative 14. If I take the negative log of 1 times 10 to the negative 14th. If I found P kW, that's 14. 14 is equal to the pKa plus the pKb. I can also say that the Ka times the Kb is equal to 1 times 10 to the negative 14. Let's look at this example where I have the ionization of a weak acid, HCN, and the interaction with its conjugate base, Cn-, both with water. So HCN we know is a weak acid. Acids are still going to donate their hydrogen, leaving me with Cn- on the right and H3O plus on the right. If I look up HCN on that chart right here from earlier, HCN's value is 4 times 10 to the negative 10. And notice that Cn-'s value, the Kb, is 2.5 times 10 to the negative 5. There's those Ka and Kb values. Looking at the Cn-, that's my base. Bases are proton acceptors. So that water is going to donate 1 H, giving me HCN on the right, and leaving H2O over here with OH-. So the Kb value is 2.5 times 10 to the negative 5th. If I multiply these two together, I get 1 times 10 to the negative 14th. If I cross off on both sides, duplicates that I have on either side, HCN, HCN, Cn-, Cn-, and bring down what didn't cross off. My H3O plus will come down, my OH- will come down, and my two waters will come down. Notice that I have my water in equilibrium with hydronium and hydroxide, which is my K expression for water. Hydronium times hydroxide concentrations is equal to Kw, which is equal to my Ka times my Kb. If I didn't know my Kb, I could find it by taking Kw and dividing by the Ka value to get the Kb value. 2.5 times 10 to the negative 5th. Looking back at that chart, see if you can place the following acids in order of increasing strength. Pause the video here. Hopefully, D, you had the lowest, because it's the greatest number. As our numbers get smaller, we get stronger acid strengths. So D, then A, then B, then C. Go back and look at those Ka values. Which is the strongest acid? Hopefully you said H3PO4. I went and looked at the values here. This was 7.5 times 10 to the negative 3 and found the other 3. And the largest Ka was our phosphoric acid. Which one of these is the strongest base? Again, I looked at the values on that page and I got carbonate with 2.1 times 10 to the negative 4th is the largest Kb.